Welcome back to Edupedia World. Today's lecture we will see about mechanical energy and the two types of energy that contributes to mechanical energy. We will discuss kinetic energy in details and we will look into the work energy theorem. Let us get started with today's lecture. Mechanical energy is the energy possessed by a body by the virtue of its position or of motion. Mechanical energy, this is energy possessed by a body by virtue of position or motion. As we can see in the definition, there are two components to it, two components to mechanical energy. One is the position and the second is the motion. So the energy, the component of energy due to the position or the configuration is called as the potential energy. Potential energy. And the component which is due to the motion is called as the kinetic energy. So fundamentally, mechanical energy is the sum of the potential energy and the kinetic energy of the body. Further in the lecture, we will see how we define the kinetic energy and how we define the potential energy. Let us begin with kinetic energy. Kinetic energy is also represented with the letter capital A, capital K, or it is also sometimes written as KE, as in kinetic energy. Now, as we already saw a little about it in the definition, that it is the energy due to the motion. So basically, kinetic energy can be defined as the energy possessed by a body by virtue of its state of motion. What we mean is that the energy component due to kinetic energy is basically due to the motion of the body. I need to rectify the spelling here. It should be P-O-S-S-E-S-S-E-D. Sorry for that. So coming back to kinetic energy, it is the energy possessed by virtue of its state of motion. Mathematically, the expression for kinetic energy is half into mass into velocity squared. This is the mathematical expression of kinetic energy. We will see the derivation of kinetic energy now. In order to derive the expression for kinetic energy, we need to understand how do we get the kinetic energy. If a body of mass m is at rest, then in order to increase the velocity to final velocity v, we need to apply a certain force such that it accelerates and reaches the velocity v. So the initial velocity is 0, the final velocity is v, and we apply a force which is equal to mass times the acceleration. Now this force will do a certain amount of work on the body during the period in which it goes from an initial velocity u is equal to 0 to a final velocity v. What will that work be? That work will be equal to force into the displacement, and this work will actually be exactly equal to the kinetic energy gained by the body, because that work is the only thing which is imparting the kinetic energy. So if we find this work W, then that W will be equal to the kinetic energy of the body. Therefore, we need to find force into displacement. We know that the force is mass times acceleration, so that is not a problem. We have the force, but to find the displacement we will use one of our equations from equation of motion. What were the equations of motion? One was v is equal to u plus at, second was s is equal to ut plus half at square, and we had v square minus u square is equal to 2as. In this set of variables we do not have time, so we will use the third expression. Now if we apply the third expression, v square is minus u square is equal to 2as, what we get is v square is equal to 2 times a times s, and as a result we get s is equal to v square by 2a. Now we have the distance covered by the body when it increases the speed from 0 to v, and we know that the force is mass times acceleration. Therefore, using this and this, we can combine the two and say that the work is equal to force is mass times acceleration, and s is v square by 2a, and this gives us half mv square. So half mv square is the amount of work that we need to do to increase the speed from 0 to v. Therefore, this work W is also equal to the kinetic energy. Hence, the kinetic energy of the body is half times m into v square. This is our expression for kinetic energy as I have expressed here. Next, let us see the relation between kinetic energy and momentum. Kinetic energy and momentum can be expressed by first writing kinetic energy is half mv square, and we know that the potential energy P is equal to mass into velocity. So from this, what we can do is we can write this as equal to half m square v square by m. So basically it remains half mv square, and then m into v the whole square can be written as p square. So that makes it half times p square by m. Therefore, we see that the kinetic energy K, let me write it as K, is p square by 2m. Alternatively, we can express momentum as root under 2 times mass times kinetic energy. So this is the relation, these two are the relations between kinetic energy and momentum. Relationship between kinetic energy and momentum. What we can see from here is that kinetic energy is proportional to the square of momentum. Now we have seen the relation between kinetic energy and momentum. We know that the relationship between velocity and kinetic energy is half into m into v square. Now let us see something which is known as the work energy theorem. The work energy theorem. What the work energy theorem says is that the work done by a force on a body increases the kinetic energy of the body. The work done by a force on a moving body is equal to the increase in the kinetic energy of the body. So the amount of work done by the force will be equal to the increase in kinetic energy produced in the body. This is the statement of work energy theorem. Now, how do we mathematically prove this? In order to mathematically prove the work energy theorem, we need to consider the initial velocity of the body as u, the final velocity as v, and F as the force which causes a work W is equal to F into S. Now, since we know that the force is mass into acceleration, we have this F. Now, what will be the distance covered S? For that, we need to go to the equations of motion, and we will use the relation v square minus u square is equal to 2as. From this equation we will find what is S. Let us do it. S will turn out to be v square minus u square divided by 2a. So if we replace S in the relation for work, and if we replace F over here, then that will give us work is equal to m times a into v square minus u square by 2 times a. We can cancel the A and A here, and that will give us half times mv square minus half times mu square. This is u square, and we know that half times m velocity square is the kinetic energy, and since v is the final velocity, this term is the final kinetic energy. Kinetic energy final, and since u is the initial velocity, half mu square is the initial kinetic energy. So what we get is that the work done is equal to the final kinetic energy minus the initial kinetic energy, and this relation of the work done is equal to final kinetic energy minus the initial kinetic energy is exactly the statement of the work energy theorem. We have mathematically proved the work energy theorem. We see how that works. We understand that the change of the kinetic energy of a body is due to the work done by a force on the body. And this work energy theorem's statement will be used while solving a lot of numericals. So this work energy theorem is a very important take-home concept from our lecture today. Next, let us see the different forms of kinetic energy. Kinetic energy can be broadly classified into three forms. The first is translational kinetic energy. Second is rotational kinetic energy, and thirdly, vibrational kinetic energy. Vibrational kinetic energy. So the translational kinetic energy is the kinetic energy possessed by body when it is moving in a straight line. The kinetic energy of a body due to motion in a straight line, that is translational kinetic energy. That would be, say, a box is moving in this direction with a velocity v, then the kinetic energy is half mv square. So that is translational kinetic energy. Second is rotational kinetic energy or rotational energy. This is due to the rotational motion of a body. Rotation. Say you have a top spinning. Say you have something like this, and this is spinning with certain velocity about an axis. It is rotating this way. Then though this body is not moving forward or backward or in any direction, rather it is hinged at a point and rotating about it, this body still possesses a kind of kinetic energy, and that kinetic energy is called rotational kinetic energy because it is by virtue of rotation. And the third type of kinetic energy, the third form of kinetic energy is called vibrational kinetic energy, which is due to vibration in a body. The origin is vibration. Say there are two masses which are vibrating in to and fro motion about a mean position. Then the energy possessed by it is called as the vibrational kinetic energy. Like let's say there is a system like this, and this is a spring and there are two masses attached. This compresses the spring and that results in a development of restoring force, which again leads the mass to move in the opposite direction. And this process keeps repeating, that is, it keeps fluctuating about this mean position, which is termed as the vibrational kinetic energy, because this kinetic energy manifests itself as a form of vibration. I will wrap up today's lecture at this point. In my next lecture, we'll see about the second form of mechanical energy, that is the potential energy, and then we will see certain numericals to understand the whole concept better. Till our next class, have a great day. Bye.